Hello, let's discuss a topic from digital electronics, that is multiplexers. Okay, a multiplexer is a combinational circuit. Alright, there are two kinds of circuit in digital electronics, that is combinational circuit and sequential circuit. We will study about this more in another chapter. What we need to know now is that a combinational circuit does not have a memory and its output depends solely on the current input. Alright, so a multiplexer is a combinational circuit. Multiplexing means many into one. That is, there can be many input signal, but at a time only one output signal is present. That is time division multiplexing. This is done using select or control lines. Because of this property, a multiplexer is also called as data selector. A necessary condition for a multiplexer to hold good is that if n number of input signals are there and m control signals are there, n should be less than or equal to 2 raised to m. If n equals 2 raised to m, it is called as a complete or perfect multiplexer. Let's see a few applications of multiplexer. They are used in parallel to serial conversion, for sending data in high-speed communication networks, in signal routing, in digital audio application as mixers, for controlling gain of analog amplifiers digitally, to implement logic functions. I would love to give you guys a small task here. If you could find out how multiplexers are used in controlling analog amplifiers gain digitally. If you have any queries regarding this, do let me know. Alright? Let's see a 2:1 multiplexer. So as the name suggests, they have two inputs, that's right, and a single output. We know that n, that is number of inputs, should be less than or equal to 2 raised to m, where m is the select line. Alright? So if n is 2, then m is log 2 to the base 2. That is, by reverse calculation, we can find the number of select line, that is 1 here. Alright? On the right side, we have this truth table of the multiplexer here, 2:1 multiplexer. For different combination of the select lines 0 and 1, we have their output here. So this is the binary equation of this 2:1 multiplexer. We can write this from the truth table. Alright. So when I1 is the output when S0 is 0, that is I1 S0 bar plus I0 S0, that is I0 when S0 is 1. This is how we write the binary equation of any multiplexers from the truth table. Alright. Let's see a 4:1 multiplexer. 4 inputs and the single output. Log 4 to the base 2 is 2. 2 select lines. That's right. We have the truth table here. We can write different combinations of the select lines 0, 0, 0, 1, 1, 0, 1, 1, and these are their outputs correspondingly. And we can write the binary equation from this. Okay. Let's see if we can get this from this. Okay. So I3 when S1 bar, S0 bar, that's okay, plus I2 S1 bar, S0, that's also good, I1 S1 S0 bar plus I0 S1 S0. Alright, let's go to another topic, that is we have a higher order multiplexer and we don't have a lower order multiplexer. How to convert this higher order multiplexer to a lower order multiplexer? Alright, this can be done in two ways. We can short circuit the select lines or we can use NOT gates at the select lines. Let's take an example of 2:1 multiplexer using a 4:1 multiplexer. Alright, so we have a 4:1 multiplexer here. We can just short the select lines On the right side, we have the truth table of 4:1 multiplexer as well as 2:1 multiplexer. So we are supposed to make this truth table from this. I mean, basically this circuit is supposed to work based on this truth table. Alright. So we just have a single select line. So, and also we have short circuited this. So when this is 0, select is 0, that is select is 0, both are S1 and S0s are 0. So this equation here, and I3 is the output. Alright, so we will connect I1 of 2:1 mux here, and when select line S0 is 1, both will be 1 here. So I0 is the output. So we will give the I0 of the 2:1 multiplexer here, and we'll get the output here. These two we won't connect, alright, or we will just short them and ground them, alright. Next is by using a NOT gate at the select line. So when select line of the 2:1 multiplexer is 0, here we will have 0 and here it will be 1. So 1, 0, I1 is the output. So we will give the I1 of the 2:1 multiplexer to the I1 of the 4:1 here. And when the select is 1, that is here it is 1, it will be 0 here. So 0, 1. Alright, so the output will be I2. So I2 is connected to the I0 of the 2:1 multiplexer. And this will act as a 2:1 multiplexer rather than 4:1 multiplexer if we connect the NOT gate to this S1 like this. Alright. Next, let's see how a lower order multiplexer can perform as a higher order multiplexer. Alright. So this is done using by cascading this multiplexer in different stages. So this lower order multiplexer can have enable or disable signal. So if they are not having enable or disable signal, then we will follow these steps. Alright. If we are supposed to make N1:1 multiplexer using N2:1 multiplexer, where N1 is greater than N2. So lower order multiplexer using lower order multiplexer, we only have lower order multiplexer and we have to make a higher order multiplexer. Alright. So the number of multiplexers required in the first stage is N1 by N2. Then number of multiplexers required in the next stage is that this N1 by N2 divided by N2. This will continue till we have a single multiplexer in the final stage. Alright. Let's take an example of a 4:1 multiplexer using a 2:1 multiplexer. Here we have N1 as 4 and 2 as 2. So 4 by 2 is 2. So this in the first stage we just have two multiplexers, 2:1 multiplexers. Then this 2 divided by 2 and 2 is 2. Alright. So we will have a single multiplexer in the last stage. And in the first stages, we will connect the lower order select lines. And when we go further, we will connect the higher order select lines. So here we have to make 4:1 multiplexer using 2:1 multiplexer. For we only have two select lines, S0 and S1. So if this is the case of 8:1 multiplexer, we will have one more stage and we will connect S2 to the final stage. Alright. So let's check one input from the truth table, so that let's check if this is working properly as a 4:1 multiplexer. So if S1 and S0 are 0 and 0, so S0 is 0. So both these two muxes are selected and I3 is the output here and I1 is the output here. These are given to this. And S1 is also 0, so only this input will be the output, that is I3 will be the output. So this you are getting. Alright, let's see next case when S1 is 0 and S0 is 1. So when S0 is 1, I0 will be the output here and I2 will be the output here, but S1 is 0. So S1 is 0, so this output is connected to here, that is here we are getting I2. So for this case the output is also right. So if you check out all other cases, we will get this truth table functioning correctly in this circuit. Alright. Okay. In several competitive exams, you might be asked to find the minimum number of 2:1 mux required to make 2:1 mux. So this is the equation that you use there. So just keep this in mind, that is 2:1 minus 1. Alright. The second case is where a lower order mux is having enable or disable signal. So in that case we follow the same steps as before. The only difference is that in the final stage there will be two muxes, and after that we will use an OR gate at the output. Alright. So let's take an example of 4:1 mux using 2:1 that has an enable signal. Here the select lines are connected as before to the 2:1 mux. The difference is that the last select line is given to the enable signal, and there is a NOT gate at one of the 2:1 mux here. Alright, and we will connect an OR gate to the output of these two last mux. Okay. Alright, so let's take one of the case from the truth table. Let's take when S1 and S0 are 0 and 0. Alright, so when S1 is 0, alright, here in this lower mux will be enabled and will be not enabled because S1 is 0. But S1 is given to a NOT gate first and then given to this mux. So S1 this enable is equal to 1 when S1 is 0. Alright. So this 2:1 mux is enabled and this is not enabled. So whatever the value of S0 is, this mux will give the output and this won't give the output when S1 is 0. So when S0 is also 0, then I3 will be the output here, and there is no output since S1 is 0 here. So the output Q is I3. That's good here. Let's take the next case. So, okay, let's take this last case. When S1 is 1 and S0 is 1. When S1 is 1, this is enabled, but here an enable is S1 bar, so it is 0. So this mux is not enabled, and S0 is also 1, so I0 will be the output here, and this is given to Q. So this is how we make 4:1 mux using 2:1 mux that has an enable signal. Similar to before, this is the equation, that is 2:n minus 2 muxes are required to make a 2:n mux using 2:1 that has an enable signal. So the difference is that one mux will be less if there is an enable or disable signal, whereas here there will be only muxes, but here in the final stage we will use an OR gate. Alright. So if we have a n variable logic function, then how many number of 2:m mux is required? So if n minus m equals 0, then no extra gate is required, and n minus m equals 1, at most one inverter is required, and if n minus m is greater than or equal to 2, at most 2 level SOP, that is sum of products, are required. So these equations are normally used in competitive exams for solving the problems real fast. With these basics, let's solve a few gate problems. In the following circuit, X is given by, so we have to find X. We have two 4:1 multiplexers. Here to the select inputs we have given A, B and C, and the output of the first multiplexer. Alright, let's find y. So y, when A and B are 0, 0, we have output as 0. When A is equal to 0, B equals 1, output is 1. That means y equals A bar B plus, when this is 1 and this is 0, that is A B bar, output is there. So and when both are 1, A B, there is no output. So y equals A B bar plus A bar B. This you can see, this is an XOR gate. So what will be y bar? Y bar is X NOR. So the equation of y bar is, we can directly write, because we found that it's an XNOR gate, as AB plus A bar B bar. This is given to here. Now let's find what is X. X is similar to Y, that is X equals YC bar plus Y bar C. So we can substitute y and y bar here and expand these to this equation and obtain x as a b bar c bar plus a bar b c bar plus a b c plus a bar b bar c. Let's find this in the given options. Okay, this is already here, only these two are here and there. So the answer is option A. The next question is, the Boolean function f implemented in the figure using two input multiplexers is. This is similar to the previous question. The only difference is that we are having two 2:1 multiplexers, and here B is connected to the first multiplexer. If this output is y, let's find the Boolean equation of the first multiplexer. That is, when this is 0, that is B bar C plus B C bar. Alright. Then this is given to the second multiplexer. Here the input is 1A when y equals 1. So F equals what? YA. Alright. 1 second. X equals YA. We can substitute y from the above and we can expand that there, and we will get F as A B bar C plus A B C bar. This is also option A. Next question is, the minimum number of 2:1 multiplexer required to realize a 4:1 multiplexers. We have already seen this equation for such a case. That is, here we have, if 2⁻n⁴ multiplexer is using 2:1 mux, then minimum number of mux required is 2⁻n - 1. So here 2⁻n is what? 4. 4 minus 1 equals 3. Answer is option 3. Next problem. What are the minimum number of 2:1 multiplexers required to generate a 2-input AND gate and a 2-input XOR gate? So we have discussed something like this before. We have to generate n variable function using 2⁻m mux. So we have these three cases. Let's solve that. So n there is 2 and m is 1. So n minus m equals 1. So at most one inverter is required with 2:1 mux. We are not provided with any inverters, only 2:1 mux. So we have to find and solve AND and XOR using 2:1 multiplexer. So this is the binary equation of a 2:1 multiplexer, I1 A bar plus I0 A. So we need to obtain the equation AB from a 2:1 multiplexer. So if we don't want this part of 2:1 multiplexer, we only want this part. So if we are giving I0 as B, then we will get Q equals AB. So that is what we have done here. I0 is grounded, so this is 0. This I1 is grounded, so this is 0. I0 is given to B. So when A equals 1, output is A, B. Alright. So for XOR gate, we have Q equals A bar B bar plus AB. So here A bar, I1 should be given to B bar and AB, so I0 should be given to B. So what we are doing here is we will make a B bar, a NOT gate in the first stage, and this B bar is given to the second stage. So here we have B, and when B is 0, I1 is the output. So we will obtain B bar here and B directly to the I0 we are giving, and we will get A bar. When this is 0, B bar is the output. So A bar B bar plus A B is Q. So here we need two 2:1 mux, and here we need a single 2:1 mux. So the answer is option A. So with these problems, we have come to the end of this topic, that is multiplexers. If you have any queries regarding this, do let me know. And please do not forget about the small task I have given before. Alright, that is to find the, I will once more remind you that task, that is you have to find how we can control the gain of an analog amplifier digitally using a mux. Alright. So, thank you.